Hey guys, all right, so this is a brand new chapter. We're going to start with 4.1, extreme values of functions. Our first definition is absolute extreme values, or some textbook will call it the global extreme values. Let f be a function with domain D then f of c is an absolute maximum value on D, which is the domain, if and only if f of x is less than or equal to f of c for all x in the given domain D. So what I mean by that is, here's our graph. Let's pretend that we have an upside down parabola. This is x, this is y, and let me just get a different color pen to find. So it says, let this function with some random domain, in this case it's just your domain is all reals, and this function has an absolute maximum, which we know it's at the vertex, okay, and here is c, if and only if this f of c is going to be bigger than every single y value out there, or at least equal to, okay? So if it's bigger than or equal to, then it is an absolute maximum. And an absolute minimum is going to be very similar. An absolute minimum value on domain if and only if f of x is greater than or equal to f of c for all x in the domain. So very similar. I'm going to sketch that out. Now I'm going to draw a parabola opening upward. And we know already we have a minimum right here at the vertex. So let's call this C. And this is going to be f of c. So the definition for an absolute minimum is if it's the lowest value of all y values out there. Okay, so again, it's the lowest y value of all y values out there. Or at least, okay, or at least it's equal to the lowest y value. So the lowest y value is going to be determined an absolute min. The highest y value is going to be called the absolute max. Now, we often don't really use, excuse me, I'm losing my voice. We often don't really use the term absolute or global. We normally just say maximum or minimum. Example 1, identify each x value at which any absolute extreme value occurs. So absolute values, meaning that it's either the highest or the lowest. So this is the highest. On that one, that's going to be qualified as an absolute max. Absolute max is, let's call this, this location right here is not labeled, so we'll label it C. Absolute max is at C. Or you can even say at x equal to C, or x equals to C. Now we also have an absolute min, which is the lowest of the lowest, since that is close. Okay, it must be close for it to exist. And if you look at the original drawing, it is close. So this right here is an absolute min at x equals to b. On example B, we can spot the highest location right away, which is right here. This is going to be your absolute max. And this one, we know absolute max has a y value of 14, so absolute max is 14. So when I'm looking for, if I say, what is the absolute max? The answer is 14. If I'm asking, where is it at? Then you want to write at x equals to 1, okay? Then similarly, we are going to go and find the lowest value. Well, down here, this is your lowest y value. So absolute min is, this looks like what? Let's call it slightly over 2. So let's call it 3. So for the sake of simplicity, we'll call it 3, okay? Is 3 at x equals to 5. So don't forget, if I'm looking for what is the absolute max or what is the absolute min, you're giving me the y value. We have our next definition, which is the the extreme value theorem. Extreme value theorem states, if f is continuous on a closed interval, let's call it all the way from A to B, then f has both max and minimum value on the interval A to B. Okay, so that means it's continuous from A to B. It doesn't have to go on forever, as long as from a certain interval is continuous and is closed on the endpoints, then as you know, there will be an absolute max or an absolute min. Let's move on to the next page. Example 2, identify each x value at which any absolute extreme value occurs. Explain how your answer is consistent with the theorem, extreme value theorem, okay? So first, let's look to see if if we have the highest of the highest. So if you look here at this very top value, that is the highest of the highest, but that's an open circle. Therefore, absolute minimum value, absolute max value, erase that. Absolute max value. My computer is frozen, so give me 1 second for that to come on. There you go. Absolute max value does not exist. Does not exist. So let's see. Okay. Because it is an open circle. Okay. Now let's go and find the lowest y value possible. Well, as you can see right here, the lowest y value possible, it's on the x-axis. So this is absolute min. Absolute min is, let's say, identify each x value. So I don't need to say absolute min is 0. Absolute min is when x equals to 2. Okay. Now the next part is important. Then it said, okay, well, explain how your answer is consistent with the extreme value theorem. Remember, the extreme value theorem said it has to be continuous in between the closed interval. Well, this function is not continuous. That's why an absolute max doesn't exist. If it is continuous and both endpoints are closed, then you will definitely have min and max, okay? So extreme value theorem does not apply because f is not continuous. Okay, let's try B. B, we can go and find an absolute max because I can see this is the highest. A max, and remember it's looking for x value, so A max is at x equals to c. Then let's look for the lowest y value. Well, when we look at the lowest y value, it's an open circle. So absolute min does not exist. Then we have to answer why it fails the extreme value theorem. Okay, extreme value theorem does not apply. Well, this one fails multiple ways. Number one, it's not continuous. Number two, the endpoints aren't close. So extreme value theorem does not apply because f is not continuous nor close on endpoints. Okay. Our next vocabulary is called the local extreme values. So let's go and get my, okay. Let C be an interior point of the domain of the function f. Then f of c is a, definition number one, a local maximum value at x equals to c if and only if f of x is less than or equal to f of c. As you can see, the definition here is very similar to the absolute value max for all x in some open interval containing c. It's not exactly the same, but it's very close. Okay, we'll definitely go through some examples so you can see the difference. Then, if C is an interior and it could be a local minimum, local min value at x equals to C, if and only if f of x is bigger than or equal to f of c for all, all x in some open interval containing c. Okay, now here are some important details that I would like to mention. Important detail number one, the word local extrema. This is, if you see this in the instruction, it's plural, and sometimes, okay, are also called relative extrema. So I remember in Algebra 2 book, or even regular pre-calc book, they may have used the relative. In this particular calculus book, it uses local. So it depends on what book you're using. But if you see the word local or relative in any, exams, it just means the same thing, okay? And then key number 2, important, absolute extremum. This is also, extremum is also local extremum. But the converse is false, okay? So if you have an absolute extreme value, absolute max, absolute min, then it's also a local extreme max or extreme minimum. But if you have a local, then it's not absolute, okay? Theorem, here we go. Local extreme value theorem. If hi, honey. If a function, sorry, that was my daughter. If a function, are you, there you go, you gotta go finish your schoolwork. If a function f has a local max, local max value, or local min value at an interior point C of its domain. So if a function has a local max or local min, and this is important, and if f prime exists at C, that means at the same x location, then f prime of C equals to 0. Super important, okay? Well, so when you think of this, what is f prime equals to 0? What is that? What does that mean to us? F prime equals to 0, meaning that that's a slope equals to 0. If a slope equals to 0, that means it's a horizontal tangent. Oh my, isn't it connecting now? But remember, this one is talking about an interior point, so not an endpoint. Next, we are moving on to the definition of critical point. Move on to the next page. Critical point, a point in the interior of the domain of a function, let's call it f, at which f prime equals to 0. What? It's repeating the definition from prior, right? As you can see. So a point in the interior of the domain of a function f at which f prime equals to 0. That means this is a, based on this definition right here, I'm not done with that definition yet. Based on this, this is called a local min or local max. Okay? So, or f prime does not exist. Okay, so the critical point has two parts. It could be when you have a local min or local max, or when you take the derivative and it doesn't exist. Example 3 for 4.1. Use analytic methods to find the extreme values of the function on the interval and where they occurred. Example A says g of x equals e to the x, and the interval is a closed interval between -1 and 1. First, what you want to do is, it says here, use analytic methods to find extreme values. So first, you want to find the critical point. So find the critical points. The critical points from the definition earlier is when the derivative is 0 or when the derivative does not exist. So first we have to take the derivative. The derivative of e to the x is e to the x. Okay. You want to solve for x because the critical point again is where it equals to 0 or where it doesn't exist. So when the critical point equals to 0, we want to solve for x. Well, obviously it's an exponential function, and in exponential function, it's never going to be 0. So this is not possible. Okay. Next step, step number 2, we want to remember the extreme values is we're looking for minimum or maximum, okay? So, and based on the definition, it's when the derivative is equal to 0, or, as you can see, by definition, the critical point when the derivative doesn't exist. And also the endpoints, right? If it's continuous, the endpoint could also be the min or max. So second, we want to use endpoints and plug into your function, f or g or h, whatever it is, okay? This is to referring back to the extreme value theorem. Well, you have an endpoint of a -1 and a +1, so we'll plug that into your regular function g of x. So g of a -1 and g of a +1. That's e to the -1, which is 1 over e, and this is e to the 1, which is e, which is about 2.718. So if you think of this, okay, your derivative was not defined, okay, then your endpoint, one of it is 1 over e, which is 1 over 2.718, which is about a third, and then this is about 2.718. So you only have 2 locations, and as you know, e to the x is continuous, so this is a continuous closed interval, and based on your extreme value theorem, we know there has to be a max and a min. I'm using the word max instead of an absolute max, and that's stated before in the definition. Max is e, which is the higher of the 2, at x equals to 1, and your minimum value is 1 over e, is what I meant to write, at x equals to -1. So when it says use analytic methods, it's asking for you guys to write it all out. And we're going to try the same thing for example 3b. Example 3b gave you k of x equals e again to the -x squared. And this case is talking about the domain of all real numbers. And similarly, we're going to start with use your critical. Find the critical points if there's any. First, find critical points. Okay, so critical point is talking about the derivative, so I'm going to use u substitution. So u equals -x squared. U prime will give me -2x. I'm gonna pinch it in a little bit because it tends to freeze on me when if it's too stretched out. Then that means my k of x equals e to the u. The derivative, which is k prime of x, equals e to the u times u prime. Okay. So let me pinch it in one more time to see if it stopped freezing on me. Okay. So with this said, I now have to plug u back in and u prime back in. So k prime of x equals e to the -2x squared times u prime was -2x. And I'm just going to move the -2x in the front just because I want it to look pretty. Nothing wrong with putting it back. Okay. Oh, my bad. U is just a -x squared. Let me erase my -2. -x squared. Erase that. Okay, and then erase this. Let me fix my x again. Okay, so currently we have the derivative, which is times e to the negative x squared. And now, remember, we have to solve for x. So let's solve for x. So set it equals to 0. Or you know what, let me spell that out for you. Solve for x. That means we're going to take k prime of x, make it 0, equals negative 2x e to the negative x squared. This is a factor. So you can take each factor and set it equals to 0. Well, this one, x is straight up equals to 0. Well, as we know already from prior example, that if it's an exponential, y can't be 0 or negative, so this is not possible on this side, okay? So currently, we have x equals to 0. That's one location. So let's move down here. Since there are no endpoints, and we have one critical point, that's what we are going to use. Now, if you have critical points and endpoints, you plug them all in back into your original equation. So second step, plug critical points and endpoints back into f. Okay. In this case, we're using k. Again, if you have endpoint, you will have to do all of them. Since we only have one, your critical point was x equals to 0, so we plug in 0 for our original, which is e to the negative 0 square, which is e to the 0, which is going to be 1. Since there's no endpoints and we are unsure what k of 0 equals 1 is, right? We're not sure, is it a min, is it a max? I'm going to use a number line. Use a number line to see if k equals to 0 or at x equals to 0, it's the highest of the highest or lowest of the lowest. So here's x was at 0, and we know k was 1, so the y value was 1. What we want to do is we want to pick some extreme value, such as k is negative 100, which is the left side of 0. K equals positive 100. You can pick negative 1, you can pick positive 1, you can pick anything to the right or left of 0. It doesn't really matter. You're just trying to see, hey, is it higher than 1 or is it lower than 1? So when k is negative 100, when x is negative 100, your original equation was e to the negative inside, oops, it doesn't look like a negative inside, here we go, negative inside 100, and then we're squaring it, so that's going to be a e to the negative. Would you agree that whatever that number is, it's a negative number? If it's a negative number, and technically you can pick 1,000, right? It doesn't really matter what number you pick on the right or left. You can pick 1,000, so it doesn't really matter. So pick one on the right and pick one on the left. So each is some negative number. Again, I said it doesn't really matter. Then what you want to do is, okay, well, what happens? You want to do 1 over e to the positive something really, really big. That means this is getting very, very close to 0. Okay. Then we're going to do the same thing to this side. And again, I've chosen 100. It doesn't really matter. E to the negative, similarly, we're going to pick 100 and we square that. And it's still going to turn out to be e to some ginormous number here, 100,000. Well, 1 over e to a positive big number, again, similarly, it's going to give us a number close to 0. Well, both right side and both left side of that location, 0, 1, is very close to 0. That tells me that this is the highest point. So what this is going to look like this, right? Something like that. So this is going to be the max. So that's what our answer is going to be. Max is 1 at x equals to 0. 4, it's very similar to example 3. Actually, the remaining examples in 4.1, they are very similar to each other. Direction for example 4 states, use analytic methods to find the extreme values of the function and where they happen. Similarly to example 3, okay, first, always find the critical point. Find critical point. Then critical point is the derivative. So that's going to be 3x squared minus 2. Make sure we set it equal to 0 because our job is to solve for it. We get 3x squared equals 2. Divide both sides by 3. So x squared equals 2/3. Then we're going to take a square root. So x equals plus or minus square root of 2/3, which is plus or minus square root of 6 over 3. And if we were to use our calculator, it's plus or minus about 0.82. Second step, it's always, the only difference here is we don't have an interval. So what we want to do is plug in your critical point since we don't have endpoints. Plug in critical point slash endpoint into your f function, your original function. Well, we only have 2 points, the plus rad 6 over 3 and a minus rad 6 over 3. So first one, we'll do rad 6 over 3, which is third root to the power of 3. So rad 6 over 3 to the power of 3 minus 2 times rad 6 all over 3. And we're going to add 4. Let's see. This will give us 6 rad 6 all over 27 minus 2 rad 6 all over 3 plus 4. Since the common denominator is 27, let's make them all into a denominator of 27. Let's make it all into a denominator of 27. So what that means is I'm going to multiply this guy by 9, and if I'm multiplying this guy by 27, so that will give us, here we go, minus 18 rad 6, and 4 times 27 is going to be 108. Now we have a negative 12 rad 6 plus 108 all over 27. We can do a couple of things. Looks like we can take out a 3. So that will give us a negative 4 rad 6 plus 36 all over 27. That will help. So negative 4 rad 6 plus 36 all over 9. And if we were to use a calculator, it's about positive 2.91. So that's just the positive rad 6 over 3. We would do the same thing to the other critical point of f. Sorry, frozen on me. There you go. F of negative. Let me wait for a second so that way it's thinking. So f of negative rad 6 all over 3. I'm going to move it up so we can see. And we're just going to do exactly the same thing. We know that the common denominator from the earlier algebraic work is 27. So I'm going to go straight there. Equals, if it allows me to write, equals negative 6 rad 6. I'm skipping the plugging in part and going straight to the common denominator. All right, let me just pinch it in a little bit. It's frozen on me. There you go. Negative 6 rad 6 plus 18 rad 6, if it comes up. No, it's not responding. That means it's frozen. Okay, plus 18 rad 6 plus 108 all over 27. It's coming. It just froze. There you go. Then from there, similarly, we combine like terms, we factor out the 3, we reduce it. This is going to come out to be now a positive 4 rad 6 plus 36 all over 9. And if we were to use a calculator and it is not responding, that means it's freezing on me again. That's going to come out to be about 5.09. Oh, geez, come on. Sorry, guys. Technology issue. Okay, so as you can see, I'm going to pinch it in so we can see both y values. One y value is at 2.91 and the other y value is 5.09. Now, don't think that the higher the y, that's automatically a maximum value. That is not always true. So since we do not know which one is the higher value and which one is the lower value, I am going to make myself a number line. I like number lines because it helps me visualize and organize my information. So let's see if it's going to let me even draw my number. There you go. Slowly, okay, there you go. There are the x locations. I'm gonna write x. We have, okay, then, okay, so first things first, we're going to write in our two x locations. The first was a negative radical 6 all over 3. The second is a positive 6 all over 3. And obviously, in between a negative and a positive, there is a 0. And all I'm doing is, hey, when I plug in a number on the left side of negative rad 6 all over 3, such as f of a negative 100, I'm trying to see, is it higher, okay, than the y value we found, or is it lower? That's all I'm doing. I don't really need to know the exact. Okay, let's go. And since I plug in 0, I'm just going to find the y value of that as well. And then I'm going to plug in a value all the way to the right side of rad 6 all over 3. Okay, so, well, f of 0 is quite easy to find. Let's find my equation really quickly. If you plug in 0 for x, it's immediately 4. So not a big deal. And we found earlier the y values of negative and positive rad 6 over 3. So the first one was, let's plot that really quickly. Okay, when x was a positive rad 6 all over 3, y was about 2.91. So I'm going to make it right there. F of 0, we just did that. That was 4, so it looks like that. Oh, I just plotted the wrong side, didn't I? Negative. When it was negative rad 6 over 3 was 5.09, so it's higher than 4. And then when x was positive rad 6 over 3 was 2.91, so it's down here. Now the question is, on the negative infinity and positive infinity, the end behavior, is it going downward or is it going upward? So that's where we're trying to find. So when x, it's a negative 100, all you guys are trying to do is really checking to see if it's going to be positive or negative. Here we go. Your equation was negative 100 to the third minus 2 times negative 100 and then plus 4. So this right here, that's the powerful term, that's the dominant term, that's the end behavior term. So because that is a negative, this will always be negative. Remember, we talked about these two terms right here not being very important or relevant to the end behavior. Then, same thing with 100. We're going to plug in 100 to the third minus 2 times 100 plus 4. So technically, you're just looking at this first term in a polynomial. So that will give us a positive. So that means it's going to go above and below. So if we were to sketch this out a little bit, this side will be going this way, and this side will be going like this. So this is just a quick sketch, okay? Like that. So if I And we can sketch that out so easily, right? Just knowing the end behavior. So now that we have the end behavior, we can now decide which one is the max and which is the min. And it's not an absolute max, it's just a local max because it's not the highest of the highest since the end behavior keeps going up forever and down forever. So we have an answer already. You have a local max. Local max is right here. Local max was, so is 4 rad 6 plus 36 all over 9 at negative rad 6 all over 3. Then local min is negative 4 rad 6 plus 36 all over 9 at positive rad 6 all over 3. And box that up. Now, some of you don't need to do the number line to visualize it or see it or write the answer, but if you have an issue with organization, then a number line is a great way. Let's try example B. Similarly, I'm no longer writing out the steps for you. I'm just going to work it through. First things first is find the critical point by finding the derivative and set it equals to 0. Factor out your 3, so that's x squared minus 2x plus 1 equals to 0. Try to see if you can solve by factoring, and your two factors are identical. So as you can see, there's only one x value for your critical point. Then the next thing is, hey, plug in the endpoints or the critical point. Since we don't have endpoints because they didn't give us intervals, so you only have one x value to plug in. F of 1. So 1 to the third minus 3 times 1 is 3 plus 3 minus 2. That's going to give us a negative 1. Again, since there's only one point, it is very difficult for us to determine whether it's a min or max. So make a number line. Here's x. We have x was 1 and y was negative 1. So I'm making that dot down here. Well, let's test the end behavior. I'm picking negative 100 and I'm picking positive 100. And all we're checking for if it's negative or positive. So again, because the first term is a cubic, so it's going to be a negative 100 to the third. That will always be negative. This is positive 100 to the third. That's always going to be positive. It means that this is always going to go on the left side, always go down that way, and the right side always go that way. Okay. Now, because your point 1 comma negative 1, okay, the point was 1 comma negative 1, by definition, it's not bigger than all the points, and it's not bigger or not smaller than the rest of the x's. You do not have an extreme value. No extreme value. Okay. Now back in Algebra 2, we call this an inflection point. That means it's not the highest and it's not the lowest. Okay. And later, in the next section, we are going to, I don't know what section it was, we are going to use the inflection point for something else altogether.